Hi, my name is Swaroop. I'm currently working as computer vision research engineer in Value Vision System, Ireland. I have around 10 years experience, mainly working on image processing, video processing, and computer vision algorithms. In Value, for the past 5 years, I have been working with the algorithms like object detection, object tracking, object recognition, free space detection, and segmentation. We have been working on these algorithms mainly to solve a very important use case, which is autonomous parking solution to a designated parking slot. We have also projects working on the parking slot detection, free space detection, which are very important because vehicle has to get feedback constantly, real time, in order to take safe decision to park autonomously without colliding to any objects surrounding the vehicle. So it is important to detect the object. It's not only detecting the object, it's also important to classify the objects as dynamic, static, or even classifying objects as cars, pedestrians, because it's a very useful information to the vehicle to take the priority according to type of object. It's also important to know whether the object is dynamic, static, or whether the object is moving towards the vehicle or away from the vehicle. These are the very useful informations which is required for real time, so that vehicle will take decision accordingly and safely park to a parking slot. We also are working on other useful cases like home trajectory, home parking by creating a trajectory using a SLAM, simultaneous localization and mapping, wherein we will learn a particular trajectory to park a vehicle to a particular location within the home. Probably it may be garage or some other place where it's safely parked. So vehicle will learn this trajectory, localize the objects surrounding, and then it will actually park autonomously without intervention of user. So these are the very useful cases on which we are working on. And coming to the nano degree, I have udacity nano degree is really useful for me in my day-to-day activities, because I was having only basic knowledge of image processing and video processing before joining Value. When I joined Value, I have been assigned with one of the very important algorithm, which is road edge detection. Road edge detection was very important because it is giving feedback for free space detection around the vehicle. Also, road edge detection algorithm was used as a feedback to object detection module to clear any false positive. False positive are the cases where object was detected even though there was no object. So road edge detection algorithm was actually helping by saying this particular region belongs to road and not belongs to object. So this was very important to avoid any wrong feedback given to the vehicle due to such false false positives. We in real time will have lot of challenges, like due to sunlight illumination, due to high textured road surface, and due to shadows. We tend to detect the roads part of a road surface as object and track these regions as object, which is incorrect, and it is very important to clean up these false positive. So road edge detection was used for free space detection as well as clearing any sort of false positive in object detection. Also, for the past 2 years, I have been involved in another interesting project, which is trailer angle detection. This algorithm involves detection of trailer tow bar from the very first frame, followed by extraction of template of the tow bar, and then tracking of the tow bar by template matching, texture detection, extracting the various geometric features of the tow bar, and tracking over a period of time to detect the trailer angle with respect to vehicle. This is another very important use case which solves multiple end user functionalities like autonomous parking of trailer, autonomous parking of vehicle with trailer, and also it helps user by providing the good visualization of the surroundings of the vehicle based on the trailer angle. For example, if the trailer is to the left of the vehicle, then it will show the mirror left view, whereas the right of the trailer it will show mirror right view. And just if it is following behind the trailer, behind the vehicle, then we have a very innovative use case, which is invisible trailer, wherein the camera is set up behind the trailer, and we will fuse the image which is coming from the camera behind the trailer to the image which is captured by the rear camera of the vehicle, which actually have a blocking point of trailer, which so user can actually see as though there is no trailer behind, and he can visualize what are the activities that is happening behind the trailer. So these are very useful use cases which requires the algorithm which I have developed for trailer angle detection. Okay, this is my introduction about my work from past 5 years in Valio. Coming to the Udacity Nano degree. Udacity Nano degree has been extremely useful for me for my day-to-day activities because I was having a very basic knowledge of image processing, video processing, and computer vision. Though I know quite a few algorithms in computer vision, uh, I was not having an entire picture of what all the various components which are various algorithms which are involved in the development of completely autonomous self-driving car. Especially for me, this self-driving car engineer nano degree was very useful because I was not knowing quite a few of the concepts which was taught in this particular nano degree, especially the term 2 and term 3, sensor fusion, localization, path planning, motion planning, algorithms. I was completely unaware of quite a few of these algorithms, except I know a bit about PID controllers and a little bit about Kalman filter before starting this course. Yeah, so this was very useful for me. This particular term we learned a lot of things about lidar and radar fusion with Kalman filter and unscented Kalman filter. Uh, and Marco localization, motion models, particle filter. So all these concepts were pretty new to me. Vehicle models and all. And also the term 3 was also very interesting for me because we learned quite a few things like behavioral cloning, I guess, is also one of the part of it. Yeah. Uh, Behavioral planning, yes, and trajectory generation, these are, and also advanced deep learning as a elective. I really like this particularly this term 2 and term 3, where I really learned quite a few things which were pretty much useful for me in day-to-day activities. Of course, even the term one was very interesting, wherein we had a little bit of deep learning there, behavioral cloning, I guess. So, uh, yes. Okay, coming to the term one, in term one, the most interesting project for me was vehicle tracking. That is the most interesting part of the term one for me. Though we have a traffic sign recognition project, and yes, and the lane detection and tracking anyway. That's advanced lane detection. Yeah, this the object vehicle detection and tracking. This particular project was the most interesting for me because this is pretty near to what we have been doing in Value, and though we have been using a much more extensive methods. Um, uh, over what is been used here, which is probably the basic method, I would say. Um, so this was very interesting for me. To start with, I would like to explain this particular algorithm, and to conclude this particular um, session. Okay, I have opened the Jupyter notebook for this particular project, vehicle detection. As you can see, there are 10 steps involved in this particular project. The very first step was to extract and organize data. We have been given with a set of images. Some of the images has vehicle and some of the images doesn't have vehicle, and we have to extract these images one by one. And then we have a step 2, 3 and 4, which is mainly feature extraction. Three methods is used for feature extraction, and all the three methods, the features from all three methods has been finally concatenated as a one set of feature for that particular image, which is used for further classification training for SVM models. Okay, feature extraction. Firstly, histogram feature. Basically, each image will have three planes, RGB plane, and all the three planes have been. We will do histogram analysis, and we'll bin and find the histogram for each color, and then these three histograms are combined to make one feature. And step 3, basically special binning, feature extraction using special binning. Special binning, in this method we actually resize the image, and we'll use the data of resized image as the feature. And then the step 4, which is hog feature, hog histogram of orient gradient, which is basically again like a histogram of gradient orientation, so edge orientation basically. So we finally combine all these three features from all these three methods to a one single feature set, and corresponding with that we already have a corresponding label for that image, and we'll feed that to SVM model to detect the way to train the best model which is fitting which will fit the best model and which is used for further prediction on the new data set. So yeah, then then the next step is the step 7, which is the new data. Whatever the images we are getting, the new images, we will divide this image into multiple search window of different size, and then we will each search window we will actually scan from the top of the image to the bottom of image, and each we will crop these windows, and then we will feed that to SVM model to predict whether there is a vehicle or not. And then once we have this different once we have this data of finally the list of images which actually has the vehicle, we will create a kind of a heat map, which actually is kind of like another kind of histogram binning of the smallest block size. We will actually have number of different blocks level at which the vehicle has been detected. So it's kind of like a then this map is threshold. For example, some of the windows may be having only heat map of which has only one, which is 1, maybe value 1, maybe because there's only one window which has detected that as a vehicle. So rest of the windows didn't detect as a vehicle, so that is a very low probability that that particular window will have vehicle. So we will threshold by using a special threshold filtering method, and then we also have a temporal filtering method where we accumulate this heat map over a certain time frame, which is temporal window. Then we will threshold temporally as well to make sure that okay, maybe there are some images just for few few time, maybe false positive might have been created on the road surface or something like that. So we can actually filter this using this heat map method. And then we finally with finally filtered, we filter a lot of windows, and finally we have very less amount of windows which is remaining as a vehicle windows. These windows by using these windows we'll calculate the centroid of the vehicle, and then we track this vehicle over the period of time. So that's the method used. And going through this code, yeah, this is the part of the code where we are extracting the vehicle and non-vehicle data. We use glob, which is extracting the path of the all the images, which is PNG images from this particular path, and then we are creating kind of a dictionary there for non-car and the car. Okay, and then we are reading one sample and displaying that sample here. Okay, then histogram feature. This is where we are actually extracting the histogram of R, G, B and features, and then finally concatenating them as I was telling as histogram features. And then okay, this color conversion is for just for experimentation, like just want to try whether different color spaces is yielding any difference in the final training accuracy. So just want to check that. So yeah, then okay, then okay, spatial binning. This is another method wherein we are actually resizing the image to a smaller size of 32 cross 32, and then we are converting from 1D to 2D to 1D, and then creating that as a feature. Okay. Then we have a feature extraction, hawk feature extraction, wherein we have to provide multiple parameters like what is the pixel per cell, and what are the number of cells per block. So all these things we have to give, and finally we'll have a feature vector which is coming out of it, the hawk function, which is used as a features. Finally we are actually combining and normalizing all these features. So this is the main function where we are extracting all the features, where we should call all the three methods basically, the bin spatial, and then color histogram, and then hawk features. So all these three methods is called here, and then finally we are actually, you can see here, the appending and concatenating all into one single file feature. So that is used for SVM to train basically. Okay, and then this particular is part of the code is just again the same, like single image feature, extracting the single image feature, the pretty much the same steps, but this is per image, test image. This was created for test image. And okay, this is the step, training SVM model to detect the vehicle. So now we have a X features, X train, and Y train ready for to be fed into the. This is what we are using is linear SVC. It's a type of SVM method, wherein we feed X train and Y train data, which is X train is basically whatever we were concatenating as a list of feature of histogram features, and hawk features, and special binning features. All these things combined together as create for each data, image data we have created, and this is what is that X train data, and Y train is corresponding label, and we use that to fit a best model which differentiate between the car and non-car images, and then finally use that model to predict on the test data. So test data is the one which is not yet fed into the model to for training. So this is the data, new data. So how the model performs on the new data is most important. So get the prediction, and then finally calculate with respect to the ground truth how much is the accuracy of the model. So that's SVM part, and then yeah, this is the function which creates the sliding window. As I was telling you that we divide the image into multiple sliding tiles, and then we slide over the entire image to find out whether there is a vehicle or not vehicle. So basically this is what is the thing, sliding window. For a given window it will generate a list of windows. It's just finally giving us the list of windows, and then the draw box, which is basically just drawing the box, rectangular box around the windows. Okay, and this is the area, this is the portion of the code where we actually creating windows at multiple levels, and finally we are merging all those levels into one window. Finally this is done here. So basically I have written a kind of adaptive window technique, because we cannot process the all windows in the image equally with equal size, because object will generally appear bigger in front of the camera, whereas it appears very small away from the camera. It's a scaling thing basically. So we need to consider that factor, and we need to use that particular factor to design our window in such a way that it's very optimal actually to detect the object. So this is what I have done here, and then search on window basically. Okay, this is yeah, okay, once we have created the window list, then each window by window we actually crop that in the new test image, and then we feed that Then we in this new test image we will extract all the features which we have extracted previously, like all the histogram features and hawk features and special binning features, everything extracts, and then finally this feature is fed into the prediction model, to the whatever the fitted model, to get the prediction. And then finally, if the prediction says that there is a car, then we append that window. So we creating new window list which actually has car in that particular list basically. And finally, okay, finally heat map. Okay, finally, as you can see here, this has a list of windows which is actually having car, and the heat map. So heat map is generated, as I was telling, we go through each and every window, and then we bin that within that region, within that particular box region. We'll bin every pixel to one. So finally generate a heat map. So okay, then filter the window basically. The heat map is set, as I was telling, the minimum threshold, maximum threshold was sent, and finally we create this logic to threshold the windows. Finally we'll have very limited number of windows which are actually the high probability of having vehicles. So this is a full video pipeline process image, wherein it starts from search window where all the prediction windows are generated of different size, and then we'll generate the heat map for those prediction windows basically. And then we do temporal thresholding. Here you can see we are accumulating the temporally heat map, and then we are actually creating a threshold on the threshold temporally as well. So you can see here, this is the heat map which is okay. And then the last oldest heat map is deleted here basically. That's all it's doing. So we are thresholding the heat maps temporarily as well, to finally create a, okay, this is on the test images. Okay, that is on the videos, and this is on the test images, the same procedure. So then after this we will have this particular demo of running through this particular program. As you can see here, these are the final set of windows which were remaining after the thresholding. There were a lot of windows here as a false positive, but because of this energy map, we actually threshold specially in temporally. We could able to achieve this performance. Still, we can see there are a lot of issues here, like there are certain frames where there is a flickering of the bigger window, and then because of that the foot point is wrong. So still this can be done much better. This can be done much better actually. So that's it. That's the project. That's all about the project. And yeah, so thank you very much for listening to me so patiently for so long time. Definitely I would like to make more and more sessions like this, to even it will help me to revise some of the methods which probably I might not be using in my day-to-day life, and I may forget over time. It's an opportunity for me to create such videos, and so that it will also help me to consume that particular topic in depth, and always keep that in. That will help me to probably even motivate me to apply those techniques in my day-to-day life. Thank you very much. That's all for the day. Thank you. Bye.